We're going to talk about homomorphisms. Homomorphisms are functions that have this property here. If you first multiply x and y and then apply the homomorphism, that's the same as applying the homomorphism to each element individually and then multiplying in the codomain. And the way to think about homomorphisms is they really just they preserve the same action. So the action in G, the binary operation, is very similar to that in H. So you have a homomorphism between two groups if there's a lot of similarity between the groups. And the kernel is just all the things that map to 0. So if you think about this, if you think back to like calculus, x squared minus 1, we often ask the question, what are the roots? What are the zeros? What are the x-intercepts? And we can do that by factoring and doing all this stuff. We get that x is equal to plus or minus 1. This here, plus or minus 1, is analogous to the kernel. It's everything that I can plug in that will end up with 0. And just like here, it's all the things you can plug in such that you get, not 0, but the identity. We can also define the image. The image is like the range from calculus. So x squared minus 1, if you were to graph this, it's a parabola, it's just down a little bit. The range would be from -1 to infinity. So that's analogous to the image. It's all the possible outputs, all the possible y values is the analog. All right, so let's look at some examples. So if you've seen isomorphisms before, some classes have them first. All isomorphisms are homomorphisms. Two groups are isomorphic if they are exactly the same. You just are kind of relabeling things. Two groups, there's a homomorphism between two groups if the groups have some similarity but maybe aren't necessarily exactly all the same. All right. So isomorphisms are homomorphisms by definition. Kernels of isomorphisms are the identity, or else they wouldn't be one-to-one, and images are the entire target group, the entire codomain. So this is a homomorphism, but not an isomorphism. Right? If you take phi of x plus y, well, that's by definition you just double the input. The input's x plus y, so we just double it. And that's equal to 2x 2y, which is equal to phi of x phi of y, because phi of x is equal to 2x and phi of y is equal to 2y. So that's the homomorphism property. Phi of x plus y equals phi of x plus phi of y. The kernel is 0 and 3, because phi of 0 equals 2 times 0 equals 0, and phi of 3 equals 2 times 3 equals 6, which equals 0 if you're in C6 or Z6. And the image is 0, 0, 2, 4. Why? Because we can just look at all these. That's a 4. So what are all these? Phi of 0 equals 2 times 0, which is 0. Phi of 1 equals 2 times 1, which is 2. 2 times 4 is, or 2 times 2 is 4. 2 times 6 is 6, which equals 0. 2 times 4 equals 8, which equals 2, if you look at things mod 6. And 2 times 5 is equal to 10, which equals 4. But notice the only numbers you ever get out are 0, 2, and 4. So that's why the image is 0. All right, so let's take a symmetric group and map it to C2, where phi of x is 0 if x is even, and phi of 1 if it's odd. So if both x and y are even, then phi of xy is going to be even. Why is that? Because an even times an even equals even, and phi of an even equals 0. And then phi of x, phi of y is going to be 0. That's for x, 0 for y. And then you add them together, you get 0. So these two are equal. If they're both odd, then again, an odd plus an odd, or an odd times an odd in the symmetric group gives you an even. So you still get 0. Phi of x is 1, phi of y is 1, you add them together, you get 0. If x is odd and even and odd, then even times odd is an odd, which is 1. And then you get even, phi of x is even, so you get 0. Phi of y is odd, so you get 1, you get 1. Vice versa too, same. The kernel is the alternating group, because the kernel, you get 0 if it's even and 1 otherwise. So when is x even? Exactly when it's in the alternating group. And phi of s, or the image is C2 because it's onto. Why? It's because phi of the identity is equal to 0 and phi of 1, 2 equals 1. I suppose that we are requiring that n is bigger than or equal to 2 here. Okay, so we have... All right, so we're going to take multiplication of the reals to multiplication by the reals to absolute value. It's going to be homomorphism. Why? If I multiply together two numbers, the absolute value, just using this part there, but equal to phi of x times phi of y. Great, so it is a homomorphism. The kernel is 1 and negative 1, because phi of what equals 1? Well, what can go in here? Either plus or minus 1 can go in there. That's the only way to get 1 out. And the output is the positive real numbers, because you can get any positive real number in there. So we can map from the symmetric group to the alternating group via 1, 2x if x is odd, and x if x is even. It's not a homomorphism, though. Okay. So I'm going to take this phi of just two elements, and I'm going to show it's not equal to phi of 1, 3 times phi of 1, 2. Let's see. That's equal to, by definition, this is even. So x is even, so we get that equals 1, 3. Phi of 1, 3, phi of 1 will give me phi of 1, 3 is equal to 1, 2, 1, 3. Phi of 1, 2 is equal to 1, 2, 1, 2, 3, 1, 3, and that is not equal to that, so that is not equal to that. Homomorphism. So here's a really important example. Probably the most important example. If you have a group and a normal subgroup stuff, I'm going to map G to its coset. G and H, if you have a definition, n of GH, but since n is quotient group multiplication to split this up, H. So in fact, every homomorphism can be considered to be of this form. So in other words, all you really need to know are quotient groups if you want to know homomorphic images. Remember, so in other words, a homomorphism tells you when groups have a lot in common, when groups are similar in terms of their multiplication. They say that they have similar structure. What I'm alluding to here on this slide is that whenever two groups have a similar structure, one is a quotient group of the other one. All right, thank you.